Okay, so in the previous video we saw what work is, and now let's try to find the work done by or on an ideal gas. So, and remember there are three processes that we are interested in. One is isochoric process. In an isochoric process, the volume doesn't change, right? So then, if you remember, work is minus the integral of P dV. But if the volume is not changing, then dV is equal to 0, and therefore the work done in an isochoric process is 0. So an isochoric process can be represented by a vertical line like this one here. The volume remains constant. There's no volume change. Therefore, there's no push. The gas is not changing, and there's no work being done. The next process in our list is the isobaric process. These are processes that have constant pressure, right? So if the pressure is constant, then when you write the integral of p dv, if this is constant, this comes out of the integral, so you get minus p integral of dv, and this is just the difference in volume. So basically, the work done is p minus p times the change in volume. If you go from an initial volume to a final volume, then the work done is minus p v final minus v initial, which is your delta v. Okay, so that is, and the area, this square here, that is the work done, and this is your delta V. Okay, so the next process is an isothermal process, and this process has this equation here, and let's see where it comes from. So you start here and you end up here. So what is the area of this curve? So let's write that we know that the work is the integral from the initial to the final minus here, right? P dV. Now from the ideal gas law, we know that PV is equal to nRT, but the T is constant, so we can write that P is equal to nRT over V. So therefore, the work is then minus the integral from the initial volume to the final volume of nRT over V, right? And all this stuff is constant, so it comes out of the integral. This is a V here. So you get that the work is equal to what? Is equal to minus nRT integral from VI to VF of 1 over V. And this integral, the integral of 1 over V, is the logarithm of V, right? So this here is going to give you, this here is going to give you this. Minus is equal to minus nRT, the logarithm of VF divided by VI. Okay? And then you can now use the ideal gas law to write nRT in terms of things that you know, for instance, PI and VI, or PF and VF. So therefore, this is the equation for the work done during an isothermal process, a process in which the temperature is not changing. So we have a question here. Dragging an object across a rough surface makes it warm or even hot. The temperature increase occurs because of work, heat, thermal energy, both work and heat, none of these. Take a minute. And it's work because you're dragging the object, right? So there is a rough surface here, there is friction here, but you're dragging the object, right? So you're doing work while you're pushing here. There has to be, or pulling here. There has to be a force that pulls the object, and that energy, that work, is being all converted into heat at the surface. So work on ideal gas processes. So we've seen the ideal gas equation, and we've seen that you can change an ideal gas by different processes: isobaric, isothermal, isochoric. Uh, so we are interested in looking at what work is being done when the ideal gas goes through a process. So and you have here two processes, process A and process B. So the area under the graph of process A is larger than the area under the graph of process B. So therefore, the work done during this process is greater than the work done during this process. So the work done during an ideal gas process is going to depend on the path followed through the PV diagram. So this path here is different from this path. So therefore the work done here is different than the work done here. During a multi-step process, or during the multi-step process of figure B, the work done is not the same as the process that goes from 1 to 3. So if I had a process that goes straight from 1 to 3 like that, so the work done during this process, this multi-step process, is different from the work done on this red process. Okay,